This video is going to cover sample size issues for hypothesis tests of a mean. So what I'd like to do is introduce a very concrete example and solve that concrete example. And then what we're going to do is see how all the steps that we took in that can be generalized by putting in symbols rather than concrete numbers. And once we do that, we're going to have some very general formulas for evaluating sample size or estimating the sample size that we're going to need in order to do a hypothesis test. Then I'll talk a little bit more about a topic called power curves, which will allow you to study these sample sizes that you're going to need more generally and work a problem with that also. So let's start with a problem here. Suppose that I want to test some null hypothesis, and just to keep things really simple, let's say we have a specific null hypothesis that mu is 10. Now, it's easier to understand these sample size issues if we assume a one-sided alternative. We'll get to the two-sided alternative later. So let's just say our alternative is that mu is bigger than 10. Now we know from previous studies that the standard deviation of the population is about 2. So we're just going to use 2 as our standard deviation. We also have reasons to believe that our distribution, the population distribution, is normal. Now, we want to use a type 1 error rate of 5%. Now, everything I've said so far is pretty standard. Now we get to the new thing. Now, when we do sample size calculations for hypothesis testing, we have to specify a magnitude of the difference that we want to detect. So in this case, let's say I'm really interested in differences of a half or more. If I'm interested in much smaller differences, detecting much smaller differences than this, then my sample size is going to have to be much larger. So let's just say the minimum difference that's practically meaningful to me in this problem is a half. And I'd like to be able to detect that with a power of 97.5%. Okay, so notice that implies 1 minus that is 2.5%. So my type 2 error rate is going to be 2.5%. So I've written out exactly what all this stuff means in this next sentence. So by this, what we mean is that if the true mean is, well, 10 plus this magnitude that we wish to detect, so a half, so 10.5. So if the true mean is 10.5, we'd like to be able to reject H naught with probability 97.5%. All right. The problem is, what n do I need to achieve this goal? So I want to go over to my document camera and draw a picture that I think will make all of this very clear. So here's the picture that I want to draw. I'm going to draw the sampling distribution of x bar. And so under the null hypothesis, the sampling distribution of x bar is going to be normal. All right, so this is my distribution under H naught, and the mean of this distribution is going to be 10. Now, just as to foreshadow where we're going to be calling that mu naught, which is the mean under the null hypothesis. I always like to write my standard deviations next to the curve just to make sure that I don't get confused. So sigma x bar in this case is going to be sigma over root n, so 2 divided by the square root of n. Now let's go draw the distribution under the alternative. Now under the alternative, the mean is going to be greater than 10, and I'm really interested in cases where this mean is equal to 10.5 or more. So if the difference between the null reference value, the reference value, and this my true mean is bigger than the half I care about it. So the difference between these two means I'm going to call delta. So delta is the minimum amount that I want to detect, and in this case, it's a half. Now, the variance of this distribution is going to be the same, so 2 over root n. Now, what I really seek is some sort of a cutoff. So I meant not to draw this through the intersection. All right, so this is some cutoff that I'm going to call C. Now, my decision rule is going to be as follows. Whenever I get an x bar less than C, I am not going to reject H naught. So do not reject H naught. But whenever my x bar is bigger than C, we will reject H naught. So that's what the C is implying. Now let's go try to visualize the other part of the given. So we've also been given that we want to use a type 1 error rate of 5%. So what does that mean? A type 1 error rate is the probability that we falsely reject a true null hypothesis. So if the null hypothesis is true, when do we reject H naught? And we do so in error. Well, it's whenever we observe an x bar bigger than C. So I'm going to shade in this whole area out here. And this area is going to be my alpha, which is 0.05. Now, what is a type 2 error? So type 2 error is when I fail to reject a false null hypothesis. So when is the null hypothesis false? Well, that's when I have this red distribution out here, and the mean is 10.5 or more. So if it's more, it becomes easier to reject. But we're just going to take the hardest case, which would be when mu is 10.5. So this region right here, I should have had my tail go out to infinity. This region right in here, in fact, I can color it if we like, is my type 2 error. So this is when I have a type 2 error, so beta equal to 0.025. So this would be the true mean is 10.5, so I'm sampling from this red distribution, but I happen to get an unlucky x bar down in this tail, which leads me not to reject H naught when in fact it is false. All right, so how do I find n in this figure? Well, let's go write out two equations. So the first equation that I'm going to write out is for this region out here. So alpha is 0.05, and that's equal to simply the probability that I get an x bar bigger than C, given that given that mu is equal to 10. All right, so it's the distribution under the null is another way to state that. Well, I'm now going to convert this x bar into a z, and so the way we do that, so since x bar is normal, we can turn this into a z simply by subtracting the mean. Well, what's the mean? It's 10, and dividing by the standard deviation of x bar. So what's the standard deviation of x bar? Well, it's 2 over root n. Now, what you want to note is that this is true whenever I have 5% in the tail. So what is the 95th percentile of a normal distribution? So this is going to be true when this is equal to the 95th percentile of a normal distribution, which I know off the top of my head, 1.645. So if you're not sure where that comes from, do a Q norm in R of 0.95, and you get 1.645. That's one of those numbers that that you should just know because it we use it quite often. All right, so let's now go solve this. So this is going to tell me that c minus 10 divided by 2 over root n is equal to 1.645. I can easily solve this for n, or for c, pardon me. So I'm just going to write this implies c is equal to, so I'm going to multiply both sides by 2 over root n, and then move the 10 over to the other side. So it's just 10 plus, what's 2 times 1.645? That is equal to 3.29 divided by the square root of n. All right, cool. Well, I've got one equation now that involves two unknowns. So I'm going to do the exact same thing for the red region. So for the red region, what we know is that beta, which is 0.025, is equal to, it's the probability that I get an x bar less than c, given that my mean is equal to 10.5. So I'm going to do the exact same thing to this. I'm going to go convert this into a z. So this is just the probability that I have a z less than. So we're going to take c minus its mean. So the mean under the alternative, the specific alternative that I have here, is the mean is 10.5. Standard deviation is the same, so 2 divided by root n. And when is this true? Well, this is going to be true if this is equal to minus 1.96. So we're going to do the exact same thing. Let's go solve this. This implies, okay, c minus 10.5 all over 2 over root n is minus 1.96. So if I do my algebra correct here, we have c equal to 10.5 now. And then this is going to be minus, what's 2 times 1.96? Well, that's 3.92 divided by the square root of n. So now, notice I have two equations in two unknowns. I have my unknowns being the c and the square root of n. So I'm going to equate, so this is what c is, this is also what c is. I can equate these two and get the answer. So let's go do that. I think I've got enough space to do that on this piece of paper. So 10 plus 3.29 over root n is equal to, let's go write the red equation over here. So 10.5 minus 3.92 over root n. So what I will now do is I'll move a 10 over here. So we're left with 0.5. I will move this over to the other side. We have a common denominator. And let's see, we have 7.21, if I do that right. I think that's right. Divide by the square root of n. So I'm going to go write the answer here. We're going to have, if I divide 7.21, we have the square root of n is equal to 14.42. Let's go square both sides, and we get n is approximately 208. All right, and so now we've solved the problem for n. If we want to go find c, we could go substitute that back in, but we really weren't asked to find c, we were just asked to find n. All right, so if we go back to the course packet for a second, let's go substitute more general symbols in for this. So mu is equal to some mu naught versus a one-sided alternative. Our type 1 error rate is alpha, so I've already written that out. Population standard deviation was 2, but let's just call that sigma. And our type 2 error rate that's been given is beta. Now remember, the power is just 1 minus beta. So, beta is 2.5%, the power is 97.5%. And then the magnitude of the difference that we want to detect is, in this case, a half. So what I've done here is to write out my two equations. So this was the blue equation, this is the red equation. We can go solve those and we end up with this formula. So let's just go write this out and plug in the numbers. So let me put this up here. Here was that equation that I derived on that previous page, and z1 minus alpha is 1.645. Z at 1 minus beta is 1.96. Now in the previous paper that I wrote out, I was using z beta, which was negative 1.96. Remember, we can go draw a z distribution here. So this is a z distribution. If I 1.96 minus 1.96, the area in this tail is 2.5%. The area in this tail is 2.5%. So this is the 97.5 percentile. All right, so my delta was 0.05. I could just go drop these numbers in. So this would be 1.645 plus 1.96 squared. Now my sigma squared is 2 squared, and my delta is 0.5 squared. And so if I do the math on this, you're going to see this is also approximately 208. The next topic that I want to discuss is a power curve. So what a power curve is, it gives us the probability of rejecting some h naught as a function of the parameter. So we typically want to look at this, how likely am I to reject a null hypothesis for different sample sizes. So we're going to fix our n and then look at how likely we would be to reject an h naught as a function of the parameter, but which we usually express in terms of this delta that I was talking about. So delta being how far the true mean is from the reference value. So let's go over to my scratch pad and try to derive this thing. So remember the picture that we had back here was I want to understand the power. So the power is this area under the red curve as a function of delta. So let's go try to write this out using very general notation. So my alpha, which in my case was 0.05, is just the probability that I get an x bar bigger than my c under the assumption that mu is mu naught. Okay, so that's the reference value for my hypothesis test. So this is simply going to be the probability that I get a z now greater than c minus mu naught. And earlier I was writing in a specific sigma. Let's just write sigma over root n for now. And this is going to be true when this is equal to z 1 minus alpha. So we can now go write this out. So z 1 minus alpha has to equal c minus mu naught divided by sigma over root n. So that looks very much like what we had before. I'm going to now go solve this. So this implies, if I multiply both sides and then move the mu naught over, c is just mu naught. And then this is going to be plus z 1 minus alpha times sigma over the square root of n. All right, well, let's now go do this for the red distribution. But instead of writing beta, which is what I did before, let's write this in terms of the power. So the power, which is just 1 minus beta, is equal to the probability that I observe an x bar bigger than c. So remember, the power is the probability that I get one of these x bars bigger than c if this is the mean. All right, so let's go write that out. Given that my mu is now, let's call it mu naught plus delta, because remember the power curve is an expression of this power in terms of this magnitude of the difference that I'm trying to detect. So this is going to equal the probability that I observe a z greater than, well, c minus the mean. Well, what's the mean? Mu naught minus delta. So that's really minus parentheses mu naught plus delta, but we can distribute the minus sign there, divided by sigma over the square root of n. Now what I'm going to do is drop in this for c. So let's go do that. This would be the probability that I observe a z greater than, so this is going to be mu naught plus z 1 minus alpha sigma over root n, and then minus mu naught minus delta divided by sigma over root n. So my mu naughts go away, and the sigma over root n would cross out with this one, and let's go write this out. I'm going to go back to blue. I kind of like blue a little bit better. This would equal the probability that I have a z greater than, I've got a z 1 minus alpha minus, this would be delta times the square root of n over sigma. All right, we're almost there. I'd like to write this in terms of the CDF of a normal. So remember that by symmetry, I can flip this around if I just change the sign of all this. So this would be delta times the square root of n sigma minus z 1 minus alpha. Now, one more thing. Here's the CDF of a normal. So delta times the square root of n over sigma. We can make this a plus sign if we use the other tail, so z alpha. And what I now have is an expression for the power in terms of delta. I'm going to fix n, so n is a constant. I'm going to fix my sigma, so this is a constant, and of course my my percentile from the standard normal distribution is also a constant. So that's where this expression comes from on that slide. Let's go look at a couple power curves. So let's go return to my example that I had before. And if n is equal to 10 versus some specific alternative that mu is greater than 10, the way these problems would get stated is, let's go evaluate power curves for different values of n. And I'll do this for a range of values that I want to compute between 0 and 1. So you can see where I'm just typing that expression that I derived on that piece of paper over there for different values of n. And so what you should note here is when your delta is very small, so if the true mean is, say, 10.1, or I drew a line here, a reference line of 10.2, it becomes much harder to reject the null hypothesis. So even though the null hypothesis is false because mu is, say, 10.2, it's hard to reject H naught because it's just such a small effect. However, as the sample size increases, the probability that I reject H naught increases. So if I'm using a sample size of 400, you can see that there's about, a 2/3 chance that I'm going to reject the null hypothesis. Whereas if I only have a sample of size 50, the chances that I reject the null are pretty slim. Now, if the magnitude of the difference, so if the null hypothesis is very wrong, so let's say the true mean is 10.6, then what you're going to see is even with a sample size of 50, it's pretty likely I'm going to reject it. You can see with a sample size of 200 or more, 200 or 400, I'm almost certain to reject the null hypothesis because the difference between the reference value and the true mean, so the true mean being 10.6, is so large that I almost can't help but to reject the null hypothesis with a sample of size 200 or more. Okay, so these power curves are often used for planning purposes of a study. I'll just point out in your textbook up here on page 341, they give us some power curves for a particular example. A lot of other textbooks will give you power curves in an appendix that can be used for planning a study. So that's very useful. So this final page gives us some formulas that summarize this. I've only derived the formulas for a one-tailed problem. You can work out similar formulas for a two-tailed problem. And so here's the formula. Let's just do one more example. We have 12 radon detectors, and we've observed values from those detectors. So I've got 12 values from them. And let's skip ahead to the part down here. Suppose that in this prior experiment, a value of sigma equal to 7.5 had been assumed. So from previous work, we know that that's the standard deviation of the population. How large would the sample have to be to have a type 1 error rate of 10% and a specific alternative of 95? So if we're going to use alpha equal to 0.05, then my z value for this would be 1.96 if I have a two-sided alternative. Oops, didn't mean to do that. So, oops, I'm going to close all those. I'm going to type numbers into this formula right here. So z alpha by 2 would be this Q norm. I got 5% divided by 2. This would be 1.96. Then the next term is going to be z beta. So this would be Q norm 0.1. So I can tell you right now that's going to be 1.282. So 1.96 plus 1.282 squared. Take your Variance squared is this term. Divide by the magnitude of the difference that you want to detect. And so we need a sample of about 23. Clearly, we didn't have enough in this sample because we only had 12 sampling units. And so that was inadequate. All right, that's it for my lecture on power calculations for determining the sample size with the hypothesis test.